Okay, so we are here for the final session. That is a extra session for the Algebra second course, and we will be discussing assignment number 11 for this uh, in this session. So it's going to be a 1 hour session. So I will try to just brief the theory, whatever is required for solving the questions, and then just give you some idea about the problems. And if you have any doubt, any query in between uh, the session, then you can ask or you can type. Okay, so let's begin. 11, so notes and assignment discussion. Okay, so 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 we will start with some properties of tensor product that was covered in lecture 1 and 2. So, uh, so lecture 2 was about the properties of tensor product and F algebras. Properties of tensor products and F algebras. Okay, so I will just list out the properties without giving a proof. The proof is already there in the lecture notes, so you can just go and see. So M1 plus M1 direct sum M2 tensor with uh, N is isomorphic to isomorphic to M1 direct tensor uh, R and direct sum M2 tensor R. Okay, so here M1 and M2 are right R modules and N is a left R module and R is a ring. Okay, so N is a left R module. So uh, you can see that the tensor product is distributive over the direction, and similar statement is true. Similar statement is true for bimodules. So if M1, M2 are bimodules, then also, and N is also a bimodule, then also this will hold. And here, in case of bimodules, uh, this will be over two rings. The ring structure will, the module structure will be by two rings. So only compatibility of the rings you need to see that if you are taking the direct sum, then the ring structure must be of what nature, and then if you are taking the tensor product with this, then what kind of similarity you need in the bimodule structure. Okay, so that ring you structure you want to see, because there are two rings involved. So otherwise, the same similar kind of statement will be there for bimodules. Okay. The second thing is M1 This tensor product is associative. That means that M1 tensor with M2 is the whatever is the resultant. If you take it the tensor with M3, that will be isomorphic to M1 tensor with the resultant of M2 and M3. Okay, so these two are the main properties. Then after that, there are a lot of definitions. So I would be just writing the definitions, and yeah. So first one is algebra over a field. What structure is said to be a algebra over a field? That we are going to see. So first of all, an F algebra. So there is a field. Uh, so maybe let F be a field, then an F algebra is an abelian group. First of all, let's say R plus. So and is with addition to this uh, abelian group structure, must have a multiplication multiplicative structure. That means there are just a multiplication. So yeah, there are just a multiplication from R cross R to R and a scalar multiplication from F cross R to R, such that so this in this multiplication is, say you have A comma B and it is sending it to some A dot B, and this is, say, alpha dot X, and then it is being alpha comma X, and then it is being sent to alpha dot X. Okay, so this is a scalar multiplication, and this is your multiplication. Okay, inside the ring. So this is such that first R plus dot is a ring. So R with this abelian group structure and with this multiplicative structure forms a ring. First of all, so R must have a ring structure, and then R with this the same additive structure and this scalar multiplication uh, thing, it must be a vector space. So R is a ring as well as a vector space, and that's why we are saying it to be F algebra, because the role that F is playing is to make it a vector space. Okay, so this structure is independent of the field. Being a ring, you don't need a field, okay, to define a ring structure. But to define a vector space structure for defining this scalar multiplication, you need the field. So that's why it's said to be an F algebra. Okay, so yeah. Then the third thing is this: there are two kind of multiplication, right? One is inside the ring and second is the scalar multiplication. So they should be compatible with each other. That means alpha dot scalar multiplication if were multiplied with this a dot b. This is same as alpha multiplied with a then dot b or a dot alpha multiplied with b. And this should hold for all alpha belongs to f and ab belongs to. Okay. So for example, one has this ring R to be MNF. Okay. So with matrix multiplication, this is matrix ring with uh, addition and multiplication of matrices. Addition of matrices and the usual scalar multiplication. So the usual scalar multiplication is alpha times any matrix is you multiply each entry of the matrix with that alpha. Okay. So this form F and F algebra because it's a ring and a vector space and this third compatibility condition is also will also hold. So it will form a F algebra. Second is R2. You can take the polynomial ring with addition and multiplication. Addition and multiplication of polynomials. The usual polynomials over F and the usual scalar multiplication. Okay, here the usual scalar multiplication means alpha times a polynomial is you multiply each term of the polynomial with alpha. Okay, so then this also is a F algebra. Okay, so now interesting thing is to see the tensor product of uh, algebras. Product of algebras. So yeah, but let write definition because it's a kind of construction you can say. Just write tensor product of algebras. That's it. So you you have R and S. We you have algebras. Then one can consider the F vector space R tensor F. Okay. So you have two F algebras R and S. So that means they have a underlying vector space structure and a ring structure. So we have seen the tensor product of vector spaces. So you just consider the vector space R tensor S. Okay. So if you forget the ring structure over R and S, you just consider them as two vector spaces, and then we know what is the how to define the tensor product of two vector spaces, and thus you just consider R tensor S, and then we will give a ring structure over this R tensor S and make it a F algebra. Okay. So you just consider the F vector space this, then we can define a ring structure on R tensor S via what to do R1 tensor S1. This is a one element, and we need to define the multiplication. R1 tensor S2 is another element, and we need to define the multiplication over the vector space R tensor S. So we have taken any arbitrary two element, and we will define the multiplication as just to multiply R1 with R2, and then tensor it with the multiplication of S1 and S2. So R1, R2 is well defined. So here this is inside R. So here the multiplication is defined because R is a ring. So here the ring structure of R will help us to say what is R1, R2. And this is S1, S2. These are inside S. So both we are using both the structures over R and S. To understand what is the set R tensor S, we consider R and S to be just vector spaces, and then see the vector space R tensor S, because we know that the tensor product of vector spaces, and then using the ring structure over R and S, we are defining a ring structure of over this R tensor S. Okay. So yeah, then one can check that R tensor S with this operation becomes a F algebra with this multiplication. Okay. So there is nothing. Uh, we are just giving the natural uh, algebra structure over R tensor S. That's it. Okay. So yeah, then it so using that it becomes a F algebra. Okay. So I think that's it from the first two lectures, and I will just tell you what is inside lecture number 3. So there they have discussed composition series. The definition is so. This definition is for simple module. Simple module. So yeah, our module M is said to be simple if it's a non-zero module first of all, and M does not contain does not admit a Non-trivial proper submodule. Instead of admit, I will write contain. It's a better word. Does not contain a non-trivial proper submodule. So you have a module, a non-zero module. If it does not contain a proper non-zero proper submodule, then we say that it's uh, a simple module. Okay. Submodule means a subset of the original module, which is a module in itself. We have already seen this definition. Huh? Okay. So then, what is a composition series? For composition series, actually, we don't need the definition of simple module, but we will read. We will need it later. So I have just defined. Composition series is defined independent of the this terminology. So it says that given a R module M, composition series for M is a sequence Mi equal to 0 to n of some modules of M such that you start with M and then make a chain of some modules and stop at 0. Okay, so this is I equal to 0 to n minus 1. So, uh, so this just simply means you have a chain M equal to M naught, M1, M2, and so on. And then you stop at 0. So this is any such chain is called a composition series. Okay. Now we say that this composition series Mi I equal to 0 say n is strict if Mi does not is properly contained. Mi properly contains Mi plus for all x. Okay. So this is the definition of a composition series. Then next we will see a refinement. So what one mean by a refinement means, let's say a composition series is where there a composition series. Let's say this the symbol I'm using is this is said to be a refinement of. So there are two series. Say I will use sigma 2, and it's said to be refinement of sigma 1 if the terms of sigma 1 can be found among the terms of sigma 2. So you have a composition series, then you just refinement means you add some more some modules in between, and then you make a new series. For example, here you might just take m naught, m2, m4, and so on. That's a composition series, and then you add m1 in between m naught and m2, and then all the terms remain same. So it's a refinement, one step refinement. Then you add m1 and m3 both. It's a two-step refinement. So a refinement is just you have a composition series, you make a new composition series by adding some more some modules in between. Okay. Yeah. Then sir, why we need refinement when composition is already there? Is there any relation? Yes. So see, in general we may have this m1, we can just take m to be m naught and m1 to be 0. Just two composition series with two elements we can have, but that won't be that much of of the use. Okay. uh, we want to refine it to the maximum so that we can understand it. The module will by the factors, and if you don't have a good refinement, then you won't get the information uh, that you want. Okay, maybe the next two definition will clarify it. So for example, first one is what is called the quotients. The quotients of composition series. So given a composition series, mi equal to 0 to n, its quotients are R modules qi equal to mi modulo mi plus 1. Okay, so for I equal to 0 to n minus 1. So you have a composition series, then you just look at the consequent factors. The consequent quotient models will be known as the quotients of the composition series. Now this, yeah. So this definition will clarify your doubt, Vivek. Jordan Elder series. So what does it means? It just a composition series. Composition series is called just highlight this. So it's called the Jordan elder. In short, we will just say it JH switch if it does not admit any proper refinements. So that means your series, if your composition series is refined to the maximum, it is not having any other refinement, then at that stage, the composition series is said to be the Jordan Handler series. That's why the refinement is there. So, so now this Jordan Handler series plays an important role. So, uh, for that only, I think the refinement is being discussed. There is a lemma which was discussed in the video lectures. It says the composition series mi I equal to 0 to n is a Jordan Handler series if and only if all its quotients are simple. Okay, so that's a crucial lemma. So your composition series is maximally refined if all the quotients are uh, just the simple modules. Okay, then there was an important theorem in lecture 4, that is Shear's theorem. We will see that after seeing the definition of uh, what is what is mean by the equivalent uh, composition series. So it says composition series mi I equal to 0 to n, and say there is another composition series j equal to 0 to so this one is from I equal to 0 to n, and this one is from um, j equal to 0 to n. And this they said to be equivalent if first thing is m equal to n, means they have the same number of uh, intermediate some modules in the chain. Okay, and the second is there exists a permutation sigma from 1 to m minus 1 to 0 1 n minus 1, such that so see permutation is a bijection map from n symbols to n symbols, right? So here already we are assuming m equal to n, so that means we can say that the map from 1 to m minus 1 to 0 to n minus 1 is a permutation. Okay, so don't worry about the here is m and there one side we are taking elements till n minus 1, and the other side we are taking elements till n minus 1, how it will become permutation. We are already assuming that m equal to n. Okay, so second thing is there is a permutation um, such that their consequent factors, that is mi modulo mi plus 1 are isomorphic here uh, with respect to this sigma. For each I equal to 1 to n minus. Now, here comes the important theorem due to She's She's theorem. So it says any two composition series sigma 1 and sigma 2 of an R module admit refinements. Here also the concept of refinement will be used, right? So admit refinements sigma 1 dash and sigma 2 dash respectively that are equivalent. So you consider any two composition series for any two composition series sigma 1 sigma 2 of an R module. They might not be equivalent, but there exists refinements of sigma 1, that is sigma 1 dash, and refinement of sigma 2, that is sigma 2 dash, so that they are uh, equivalent. Okay. Yeah. Next is lecture 5. In lecture 5, there was some chain conditions discussed. We just find them also because they are also needed in solving the assignment. Here, I am assuming R any ring M and R module, and yeah, then M is set to satisfy the ascending chain condition, that is ACC, if for every ascending sequence of some modules of some modules of M there exists some natural number such that this sequence ascending chain of the sequence of ascending chain, sorry, the ascending chain of uh, some modules, it terminates. Terminates means uh, after this natural number n, everything is same. Okay, then in the same split, one can define a descending chain condition. So there is nothing. In fact, I can just copy paste it and then do the necessary change. Won't be possible. Okay, let me just write it. It's essentially the same, only the uh, some changes needed. So M is set to satisfy the descending chain condition, that is DCC, if for every sequence M1, M2, of some modules of M, there exists N belongs to N. So in the above definition, we are having an ascending chain. Here we are having a descending chain, and we are demanding the same, that after some net stage, this chain must terminate. Okay. Okay then. Uh, Example: the Z module satisfy ACC but not DCC. You can check. Okay. So why not DCC? Because you consider start with Z, then you can embed 2Z inside it, then 4Z, then 8Z, and so on. Okay. So it won't be terminate if you take it just uh, like that. Z, 2Z, 4Z, 8Z, then 16Z, and you can continue. And this sequence won't terminate, right? Or ACC, you start with any submodule, then it has finitely many submodule inside it. For example, you start with some NZ. So a module will be a subset of it if it is of the form some n times uh, uh, PZ, right? Oh, sorry. This ACC, we want this. So, yeah. So, let's say you start with some NZ, then it can be embedded inside, say, something which is uh, bigger than that, but at max you can reach till Z. For example, if you start with say 8Z, right? So 8Z can be embedded in 4Z, then 4Z can be embedded in 2Z, and then after 2Z you have to stop at Z. You cannot go ahead. Okay, so this M1 would be contained in M2 if M1 is of the form say NZ, and M2 is of the form MZ, and M divides N. And there are finitely many factors for N, so it at max can include only finitely many terms in the sequence. Okay, so that's why this you cannot get an infinite sequence. So it satisfies ACC but not DCC. Second thing is the module QZP. This is X belongs to Q1, QZ. Oh, oh, yeah. q modulo z such that pnx is equal to 0 for some n greater than equal to 0. So you can check that it satisfies DCC but not ACC. Okay, I leave it to you. Then there is an exercise, very important exercise, which says that a Z module satisfies the ACC as well as the GCC if and only if it is finite. So in the first two example we have seen, here the DCC was not there and here ACC is not there, and both of them are infinite modules. And this exercise says that something will be set, a Z module will satisfy both of them if and only if it is finite. Okay, so you have examples, a lot of examples where both conditions are being satisfied. Okay, so that's it from lecture 5. Lecture 6, uh, I just I think we can uh, discuss 6 and 7 also. This is not big, but this won't take much time, but it is very crucial. So yeah, so lecture 6 has a lemma which says if M satisfies the ascending chain condition, then M admits a maximal proper submodule. Proper submodule, if you don't know what is a maximal submodule, so maybe this will help you. So N proper submodule of M is maximal proper. It is already proper if and only if there does not exist any submodule between N and M, and that is if and only if M modulo N is simple. Okay. Then at last we have what is called yeah. So we have seen the Jordan-Helder series, but we have not said about whether it exists or not. So the next uh, thing is to construct a Jordan-Helder series. So construction of Jordan-Helder. Okay. So if M satisfies the ACC and DCC condition, then we can construct a Jordan-Helder series in the following way. So step 1, you can take M naught to be just M as defined, and if M naught equal to 0, then you are done, right? Because there won't be anything between M and 0. So just M naught is a Jordan-Handler series, and if m naught is not equal to 0, m naught, that means m is not equal to 0, then by the above lemma, since the module satisfy ACC, above lemma says that if M satisfy ACC, then the M admits a maximal proper submodule. So it's not equal to 0. So then we can get it something between 0 and M naught. Okay. If it is 0, then the maximal module is 0 itself, right? So uh, the above lemma won't help much. But here the M naught is not equal to 0, so there would be certainly between something between M naught and 0 by the above lemma. So by the above lemma, there exists M1 such that uh, M naught properly contains M1 and M1 is a maximal proper submodule, right? And so there can't be anything between M1 and M naught. So this part is okay, right? For the Jordan handler part, we have to now find some modules of M1, right? The maximum refinement we have to do. So it there can't be anything between M naught and M1 because M1 is a maximum proper submodule. Okay. So step 2 is if M1 is equal to 0, then you stop it here because you have started with M naught and ended at 0 and it's maximal proper, so there won't be anything. So it's a Jordan handler series. So then M naught, M1 is a Jordan handler series. Else, so else means if it is not equal to 0, then by again, then else by the above lemma, there exists M2 subset M0 is side M1 and you have M2 here and M2 is maximal proper. Okay, so again you get is maximal proper. So you do the same thing again that if M2 is equal to 0, then your uh, M0, M1 and M2 is a Jordan handler series and otherwise you will find M3 and so on. Okay, so this will continue and this process stops. This process stops because we have assumed that M satisfies DCC. ACC was required to apply the lemma and DCC is required so that the process stops. Okay, and as we are taking the maximal proper submodule at each stage, so uh, we will get stops because we have assumed that M satisfied DCC and it will result in a Jordan handler series of for okay. That's how you can construct a Jordan handler series, provided the module satisfies what to say uh, ACC and DCC. Okay. So yeah, in lecture 7, I will just discuss this important theorem, and which says that any two Jordan-Haider series for an R module M are equivalent. Okay, and then the corollary of this construction, you can say that if M as a Jordan-Haider series, then it must satisfy then it satisfies the ACC and BCC. Okay. Okay. So that's it from the theory part. So we have already exceeded the time, but we will see some questions. Maybe not much. Then let's say first five questions we can see. Or if you have any, if you want to discuss any specific question, then also you can say. Total questions are, I think, yeah, 16. So we won't be able to discuss all of them. So if you have any particular choice, then you can tell me. We will discuss that question first. Otherwise, we will discuss first five. No. So if you don't have any particular choice, then I will discuss the first five questions. So it says let R M be an R module where R is a commutative ring. Okay, Vivek, you are saying question number 6. So okay, okay, we will see. So let M be an R module where R is a commutative ring. One has to choose all correct options. So C, Rn is an R module and M is also an R module. So M tensor R will be an R module, and any R module can be given a structure of RR module, because if R is a commutative ring, right? So R is a commutative ring means any left module is a right module. So you can have a left R module structure as well as a right module R structure. They are just the same. So the pi module structure will come from there, right? In the last lecture we saw. Okay. Then for this you just use uh, this is correct. This is not correct. Why? Because M tensor R Rn is what? This is just direct sum R n many times. So this will be just M tensor R direct sum M tensor R n many times, right? And what is M tensor R over R? This is just M, right? We have seen this. So this is nothing but M direct sum M n many times, and which is just isomorphic to this, and this is so this is just Mn. Okay, so this is isomorphic to this because M tensor R is isomorphic to M. So yes, second part is correct and third part is not correct. This is isomorphic. Okay, so maybe we can directly go to question number 6. Anyone add anything else? If you want to discuss, then it's okay. Otherwise, we will discuss 6 and stop. Okay. We have already exceeded the time. Okay. So 6 question says, let MR be the functions from R to R with pointwise addition and multiplication. This set, so you consider the set MR, which is just the maps from R to R. This is a ring with pointwise addition and composition. Then phi be a map from R to MR such that phi R is FR, and FR is just multiplication of an element of the ring by R. Okay, so it's just a, multiplication map with the const with uh, some constant R. So one has to choose all the correct options. First is phi is a ring homomorphism. So yeah, first is ring homomorphism. What one has to do? One has to check that phi R plus R dash is phi of R plus phi of R dash. So this is nothing but F R plus R dash, right? And F R plus R dash over X is equal to R plus R dash X, which is Rx plus R dash X, which is just FRX plus FR dash X for all X belongs to R. And this implies uh, FR plus R dash is equal to FR plus FR dash, which is nothing but phi R plus phi R dash. Okay. Similarly, one can check that with respect to multiplication also it will hold, because you can simply say phi FR R dash is what? It's just FR times FR dash. Okay. So uh, similarly, phi R R dash is phi R times phi R dash, and thus first one is correct, right? It's a ring homomorphism. Second is image of phi contained in the center ZMR. Uh, that won't be true, and because image of phi is not in the center of MR, this section will not make it a R algebra, because making it an R algebra, you need image of phi must be contained inside ZMR. So you just check that image of phi is not inside the center of MR. It won't be true, and just because this is not true, this will also not be true. Okay, so A first option is correct, and second and third is not correct. Okay, so if you quickly have any doubt in any of the problem, then you can ask. Otherwise, we will stop here. No? Okay then. So some chat has come. Fifth question. Okay, I will just give some hint. See, fifth is just checking. It's just computation. You just need to see that it is a vector space and ring. It's just computation, na? And we have already seen that it's both the example. In fact, we have seen MNC and PX. This is the example of F algebra that I gave, right? In the beginning, I gave this example. This will be a ring with the matrix addition and matrix multiplication. Matrix ring forms a the collection of all matrices over a field forms a ring, right? That is called a matrix ring with the addition of matrices and multiplication of matrices. And the scalar multiplication is just uh, alpha times some matrix, say Aij is nothing but you multiply alpha with everything. So with this, it will form a vector space, and alpha of AB is you can write alpha of A times B, and that is same as you multiply A with alpha of B. The compatibility thing is also there. So it will be a it is easy to see, like means matrix ring, I think you already know. It's just addition is component wide addition and multiplication is the usual multiplication. With that, the collection of all matrices forms a ring. And then vector space, for vector space, you just have this usual multiplication. Similarly, for polynomial ring, the addition is the addition of polynomials, and the multiplication is just to multiply the polynomial xn times xm, x raised to n will be x raised to m plus n, and you just linearly extend this multiplication. This will be the multiplication, and in this case the alpha of fx is just mm, say if alpha is your polynomial is of this kind, summation of ai x raised to I, then you just multiply each term with alpha. This is the scalar multiplication, and again, the compatibility thing will be there. It forms a C algebra. There is anything to check. These are the example that we gave in the beginning. No? Okay, okay, then I will stop here. Best of luck for your exam. Okay, okay, Vivek. Thank you for your, nice comment. I will stop here.